Guess we'll start. Hi, everyone. Thank you very much for coming. Welcome. I hope you're having a great TechEd. My name is Jan Gray. I'm an architect on the CLR performance team. I'm joined with my colleague, Abhi Khune, who's a dev lead on the CLR performance team. We're going to be talking about how to write faster managed code. This talk is kind of a soup to nuts tour through the most important ideas that you need to build and deploy faster managed code applications. Because we got a lot to cover in about 70 minutes, there'll be places in the talk where we refer you off to a white paper or a blog or a tutorial. So here's the outline of the talk. The first couple of slides will talk about performance engineering in general. Then we'll have several slides that motivate the move to managed code and talk about how managed code performance differs from native code performance. There'll be quite a few slides that talk about the new challenges in managed code, particularly the move to automatic memory management and some of the interesting problems you can run into there. Then we'll have a number of slides on other pitfalls that we've seen people have in using managed code. At that point, Abhi will come on and he'll show some tools that you can use to diagnose performance problems and figure out where in your code you need to make a change to get better performance. In the last couple slides in the talk, I'm going to review what we're working on in Whidbey, the VS 2005 product, to improve the performance of the CLR, and then look ahead to Windows Longhorn and what we're doing there. Okay, so why are you all here? It's because you have passion about writing fast software. You think, like I do, that slow software just stinks and you don't want to perpetrate it on your users, your customers. So what are some symptoms of performance problems? UIs that lock up, whether it's splash screens, progress bars, wait cursors, or just completely locking up. Or applications that are bad citizens on the machine, that peg the CPU, that thrash the disk, or gobble up a lot of working set, a lot of memory. Or on a server, applications that don't scale up to the load that you hope that they can handle. So what are some causes for poor performance? Sure, there's some technical reason, whether it's a mistake in designing your application architecture, maybe you didn't make the right choice in your algorithms or data structures, data representation, data placement. Maybe you have too many layers of abstraction, etc. There's some technical problem. But how is it that slow software gets out the door and into customers' hands? That's more of a sociological problem. You know, we're often very busy thinking about bugs and specs and features and meetings and schedules and stuff. We sometimes forget about performance as a feature, as an expectation of a snappy application can mean a lot more than some other little jazzy feature in your application. Just having very, very good perf, users really value that. So one thing we do is we forget about what the performance of our software is. It's the kind of thing that can get on us gradually, the death of 1,000 cuts. As features come in, the app gets a little bigger, gets a little slower. Or another thing that happens is you have an attitude like, well, once I get all these correctness features in, I'll go and attack performance kind of close to the ship time. Another thing that's interesting is if you met your boss in the elevator and he said, Smithers, how's the performance on your stuff? Do you know where it's at? Do you know what your startup time is, or your working set, or what the kind of response time your users are seeing? And do you even have goals about this is the number that we have to hit to make acceptable performance? So assuming that you've done those things and you do care about optimizing and tuning up your software, how do you go about that? Some people have said that premature optimization is the root of all evil. And there's something to that. You don't want to go and do all kinds of clever hacks and tricks all over your code for performance if those places are not where your performance problems are. In some cases, you don't want to go and tune up parts of your software where there's no performance problem. So the key question is, how do you optimize the right parts of your software in the right places at the right times? And I think you need to have a performance as part of your development process. This is a discipline that you can adopt, and I'm going to kind of give you a summary of some things we do inside Microsoft in some of our teams to get good performance. Andy Grove of Intel has said that which gets measured gets done. And it's true that if you're measuring things, you know where you stand. And it's very true in the performance space. Our mantra, if you can remember one thing from this talk, it's that you want to set high goals for your software. You want to be able to measure where you're at all times. And you want to understand and know the cost of the platform and the APIs that you're building on so that you can make good choices. In terms of what you can do in your development process, in the planning phase, you should have perf budgets, which is how much time am I willing to spend to start up my application? How much memory should it be using when it's running? What's the response time that I'm willing to tolerate? Those kinds of things. Any given application will have some numbers, and you want to go and have a good sit-down talk about what they should be. From those, you can extract goals. Goals like, for this subsystem, we need a certain amount of time or memory target to get to. And from those, with those goals, you should then go and capture those goals in automated performance tests. Now, I assume that you have development labs that go in, when you do a build, you then go and run a gauntlet of regression tests. What you want to do is add some performance tests into those regression tests. So each day or each week when you get a build, you run those tests and you know already how you're doing against your goals. Over time, you can track those trends and you can see if you're on a good trend line down to meeting the ship goals that you wanted for yourself, or, as is often the case, you're diverging, in which cases you want to put more priority and maybe more development resources on performance until you get back on the trend line that you want. In some cases, you'll have put a feature into your product, and no matter what you do, it's just not going to deliver the performance that you want. In those cases, you should be prepared to cut the feature because it's not giving good value for the user's time. I claim that if you do these kinds of things, if you're tracking your performance, if your developers can see what the overall performance health of the product is, that will help build a good performance culture. Your users will come to expect nothing but snappy performance. And they'll let you know if something's getting too slow. And your developers will start to look on performance and great performance features as kind of a correctness issue, just like any other bug. So when they make some check-in and things go south, you know, that you get a bug rated and they go and fix it and get that performance back. There's a really good, about 45-minute talk that our colleague Rico Mariani has given called Thinking About Performance. There's a reference to that at the end of the talk. I encourage you to go watch that video. Okay. Enough on general performance engineering. So you're either in the process of moving to managed code or you're using managed code in your shops. So why are we doing this transition at all? You know, we have all this native code. I think that the managed code platform is a nice step forward for software engineering. I think that in my experience with using it, it's a more productive place to do work. I can get more code. I can get more functionality written with less lines of code. Because we have this CLR, this managed execution environment, it's protecting me from some kinds of bugs that I used to get in native code, like stack overwriting or heap corruption. So I don't have to come in at 3 a.m. to go and figure out what's going on with some heap corruption issue. The managed code platform also comes with the .NET framework class libraries, and by the time we get to Windows Longhorn with the new WinFX class libraries. And these are all pretty modern and well designed and have learned, you know, building on past mistakes to get a nice clean result. And this code is good for targeting new requirements such as web services. Ultimately, I think a move to this platform will get us, in the whole world, better software, better quality, and sooner. But of course, for all this goodness, this is a different world than running in native code. And some people have observed that performance on the managed code platform is a problem. I'm going to try and correct some of those perceptions in the next couple of slides. I think the reality is that the managed code platform is a place where you can write very fast, very snappy software, but you have to avoid some problems that we'll be talking about. Okay, so when you're running managed code, if you happen to be running some ASP.NET thing on your server or some client app, and you just kind of stopped to the machine and took a look, you would find that you're running native code just like native code that came out of your C++ compiler. Sometimes it's a call into the CLR itself, but almost always you're running native code that you wrote. Now, what you wrote, of course, is VB.NET or C# code. It was compiled by a compiler down into an assembly that consists of IL and metadata. And that's not what gets run. When your application is launched or when that assembly gets loaded, the just-in-time compiler converts your IL into native code. And it's actually quite a good optimizing compiler, and it does most of the classic optimizing compiler optimizations. I won't read the long laundry list there. But the code quality is, while not as good as an offline, take-your-time C++ optimizing compiler, is quite credible, is quite good. The difference between them is sometimes the difference between other machine variations. You know, it's 10% one way or the other. The CLR also has a different way of doing memory management. It's automatic, and we'll be talking about that in a couple of slides. But the takeaway here is that the garbage collector that we're using is very fast, it's self-tuning, and it can support very high rates of object allocation and freeing. In my experiments, just on laptops, I can see allocating and reclaiming up to 50 million, 100 million objects per second, or aggregate object allocation rate and collection rate of about a gigabyte per second. So I have a couple of demos to underscore these 2 points. The first one is going to give you some idea about the JIT code quality, the quality of the generated native code. And the second is going to compare and contrast native and managed memory allocation rates. So I have to go over here. Great. So, in fact, the first thing I'm going to launch here is Managed Quake, which is a first-person shoot-'em-up game. And this code was originally at id, and they put it out under some open-source license. The folks at Vertigo Software took the C code, converted it to C++, then compiled it with the the native Microsoft C++ compiler, and they compiled it as managed C++. And that's the code you're seeing here. This is a managed C++ application. What came out of the compiler was IL, and we loaded it, JITted it, and we're running it here. This is all software rendering. I can show you that here. Let's see. I don't know if you can see that, but it says software there. This is not hardware accelerated. And I think you can agree that if we're drawing all these pixels and doing all this stuff, you're getting pretty good code quality. Now, if you actually compare the native and the managed Quake 2 versions, which I won't bother doing here, they're very close in speed. On some machines, the managed Quake is actually faster, and it's an interesting question as to why that is. Okay, so that's the code quality demo. Let's see if I can shut this guy off. What do you think? Was that pretty fast? Pardon me? Oh, sorry. Okay. All right, the second demonstration, this is just a toy application I wrote yesterday. What I've done is I build an array of 10,000 random integers, and I then insert it into a binary search tree. So I originally wrote the software in C#. I'll show you what it does in a moment. And then I converted it to C++ as faithfully as I could with as few changes as possible, and then I compiled that with the C++ compiler. All right, so here is the test function main. We make the 10,000 random integers in an array. And then we loop over 500 iterations of taking a timer, noting the time, inserting these keys into my tree, making a new tree, and then stopping the time. And then I do a little bit of statistics gathering, counting the number of microseconds each iteration took, noting the minimum and maximum time. And if I may, just for a moment, I'd like to show you how we do these timings. I have this timer class down here. And I'm calling out through pinvoke down into kernel32.dll to call the API's query performance counter and query performance frequency. Together, you can use these to get very high resolution timing numbers, which are often better and more precise than ticks. So to start the timer, we just note the time, and when we stop the timer, we note the stop time, and the elapsed is the difference. It's quite simple. Okay. So I'd also like to just briefly show you this code to show there's nothing remarkable. I'm making a tree object, which is kind of a node in the tree. It's got an integer key, and a classic binary search tree, it's got a left subtree and a right subtree. We've got a constructor. The function that inserts a new node into the tree walks the tree to preserve sorted order. The left subtree keys are always less than the root, which are always greater than less than the right subtree keys. So it loops down, walking the tree, finding where it should insert, and then it inserts it. Pretty unremarkable. To insert them all, we just insert them one at a time. Note that for each key we're going to insert in the tree, we make a new tree node object. So there's some memory allocation there. Okay, not too remarkable. So I'm going to go run this now, which I think I do here. And I'll just run it again. Okay, so what we see here is to do those insertion of 10,000 nodes into the tree, we took on average, 2.2 milliseconds. It was as quick as about 1.7 milliseconds. Sometimes we took quite a while, and I'm not sure if that was running the garbage collector or whether that was being interrupted and doing something else with a context switch. Now, let's go look at the C++ version of this. Native trees, I called it. As you can see, it's quite similar. I fill in an array of random numbers. I insert my keys. It's almost the same timer class. I'm using the same measurements. And then an interesting difference is here in C++, the node which has a key on the left and right, the C++ object is 12 bytes in size. But the managed object, which has these 3 fields of 12 bytes, also has 2 hidden fields. It has the method table pointer, which is used for virtual function dispatch and so forth, and it has another hidden field. So the managed code objects are actually a little larger. They're 20 bytes for each one. But otherwise, it's very similar code. So now we'll just run this. And it took a bit longer to allocate these objects and build the tree. And I attribute that to the free list allocator that's behind the operator new that we use to make the objects. But actually, going back and looking at the code, there's a difference between this. It's not quite apples to apples, because in the managed code implementation, I newed up the objects, and of course, the garbage collector will collect those trees when they're not used. But in the native code version, I also have to free this storage, otherwise I'll have a leak. So I'll have to put a delete tree in here. And then I'll just show you the destructor for these guys. The destructor recursively walks the tree, freeing the left subtree and the right subtree if there are any. Okay, so I'll just rebuild this. And I'll rerun it. And of course, it won't take less time. It takes a little more time. So here we see that the managed version was actually considerably faster than the native one. And I attribute those differences to the high-performance garbage collector that the managed code is able to take advantage of. So in summary, there's a chance that the managed code can have comparable performance to the native code. And we can't use the fact that we're running in managed code as the excuse for why our managed code is slower than our native code version. There may be some other things that we'll talk about. Okay. So again, I claim that managed code can be quite close to the hardware. I've written a rather long paper that's on MSDN. You can go read, which kind of looks under the hood and considers, if you're a real techie, it looks at how virtual methods are called, how casts work, what write barriers are, what bounds checking does to the runtime, etc. So, okay, so the raw platform's pretty fast. There are some differences with respect to native. If you took your native Hello World app and you moved it to managed code, you did a console.write line, you would find that it doesn't perform as well as the native version. There's additional startup costs, and there's additional working set, because the managed version has a very nice statically linked little printf statement. The managed version has to load the MS Core Works, which is the CLR runtime, and it has to load the MS Core lib, the base class libraries, and possibly system.star, etc. And the managed version also has to use to load and run the JIT compiler to compile each method as it's called. So those things add up. And so you may notice in managed code that the base cost of starting up the process and the memory footprint are several megabytes larger than the managed code version. We're working on these problems. And as you'll see later in the talk, by the time we get to Windows Longhorn, I believe that they'll be mostly past us. Okay, so we got this fast platform, yet the experience of most people writing managed code apps is that it's still not easy to get really fast code. What are some of the problems here? One is, admit it, we're all newbies in managed code land. Maybe we've been writing managed code for a year or two, but we just don't have the gut feel, the depth of knowledge that we had in native code when we knew what the C runtime libraries cost, etc. At this point, we're all kind of busy learning how to do things. How do I get from an A object to a D object, or how do I get that page rendered, or whatever? And we're not stepping back and saying, well, how much does that cost? I wonder if that's fast enough for my setting. And I also claim that if things are easier in managed code, it's also easier to shoot yourself in the foot, and you have to watch out for those things. So the theme of the next 8 or 10 slides is to avoid pitfalls. I'm going to show you some things that we see people run into over and over again, and hopefully you'll recognize these in your own code and say, oh, Jan told me I shouldn't do that, or I should think twice about that. Some of the pitfalls are new and unique to managed code, and you won't have run into them in your native code. Other ones are the same performance problems we've had from time immemorial. But there's something about managed code that in some cases exacerbates the problem. Okay, I've got a couple of slides that talk about the garbage collector. Many, many performance problems originate with people not taking the best advantages of the garbage collector or running into some problem with it. So we all have to have a pretty good understanding of how the garbage collector works. The concept of garbage collection is that there's automatic memory reclamation. In the native code world, for every new, you do a free. But in the managed code world, you just new things, and the system notices when objects are no longer reachable by your code. Those objects are just waste, and we might as well recycle their storage and put them to better use. And that's what the garbage collector does. In detail, as you allocate objects, when you say new this, new that, etc., every once in a while, the garbage collector figures it's a profitable time to do a garbage collection. At that point, it will stop all the threads. And since we're a managed environment, we know where all the object references are in memory. So we can walk all those references and mark objects that are reachable still by the code. Objects that are not marked are not reachable, they're just waste, and we want to recycle that storage. The way we do that is we compact all the live objects together, slide them all down, give them new memory addresses. And then the remaining storage is all one nice contiguous free zone. The garbage collector is self-tuning. It monitors how previous garbage collections have done and how much storage was reclaimed by the last one. It knows how much free space there is how much free RAM there is on the machine. It even knows how big the caches are on the machine. And it uses all this stuff to figure out what's a profitable time to do it. And you really should let the garbage collector make these decisions as to when collections happen. So the garbage collector is managing this heap of managed objects. Now, if you have a very large server application, it's conceivable that you have 100 or 500 megabytes of managed objects. And we don't very often want to go crawling through that whole object reference graph, because that'll take a lot of CPU time. The generational hypothesis says that most objects are temporaries, and they die within a very short time of when they're created, within a few milliseconds or maybe at most a second. And we take advantage of that fact or hypothesis in the implementation of the garbage collector. The GC heap is divided into zones. And the zone called generation 0 is where live objects are born. We will collect in that zone much more often than we'll go and collect the whole heap. I've got an animation that shows that here. So this is a scenario where I've just made a bunch of green objects. These are new objects in the generation 0 heap. The red things are object references from various places that are pointing into those objects. As the program runs, some of those object references go away. You returned from that function, and the local variable is no longer referencing that object on the heap. As you continue to allocate objects, as I said, the garbage collector will start up and say, oh, this is a good time to do a collection. So the first thing it does is it walks the current roots, which are stack variables, static variables, those kinds of things, and it goes and it marks all those objects in the heap as alive. Objects that don't get visited are dead, and the garbage collector just slides all the remaining live objects down together. That frees up this continuous zone over here, which is now the new generation 0. And then allocation resumes, threads are unblocked, and we do more allocations in generation 0. Okay. So as I said, we have this generational heap. We actually have 3 generations. Generation 0, which is approximately sized at the size of your cache typically. Because the objects often don't even leave the cache, you can get very good performance. As I'll show later, when you leave the cache and go to main memory, your performance can get very slow very quickly. Objects that survive a generation 0 collection are moved into generation 1. And much less frequently, we do a generation 1 collection. And objects that survive are still referenced in generation 1, get promoted into generation 2, which is the bulk of the long-lived objects. Every once in a blue moon, we'll do a generation 2 collection, and those objects that are still alive are called generation 2 objects. We also have a special area called the large object heap for objects that are larger than about 80K bytes or so. Those are managed with a different free list regime, and they get collected during generation 2 collections. There are actually 2 garbage collector strategies or algorithms used in the CLR, depending on where you're using the CLR. Most of you doing client development automatically get the workstation GC. This is the self-tuning there is tuned to minimize pause times. On a server where maybe you're managing larger data or more transactions, the server GC is used, and that one is optimized for throughput. It's also very friendly to multi-threaded parallel machines. So if you have an 8-processor machine, the server GC is tuned to take advantage of that. It tries to keep object allocations on the same thread and the same machine where the other object allocations in that area happen. If there's a garbage collection, it will, in parallel, use all of those CPUs to go and do parts of the garbage collection algorithm. There's some nice articles, a couple of years old, by Jeffrey Richter in MSDN that goes into this stuff in more detail. Okay, so that's the background on garbage collection that you really should understand. What are some problems that people have moving to this new garbage collection regime? The first is that even though you're not freeing objects explicitly, object lifetimes still matter a lot in terms of the kind of performance that you see. As I said, short-lived objects are really cheap. We do only a few instructions, maybe 10 instructions, to allocate an object from that Gen 0 heap. We don't have to search any free lists or anything like that. And then to free these objects, we don't do anything. We don't visit them. We don't see them. They're free to free, almost. Also, long-lived objects, if you create some objects at startup time and then they get promoted to Gen 1 and then a minute later they get promoted to Gen 2, those objects just pile up in Gen 2. They don't cause garbage collection pressure, and they're fairly low cost too, except that they're taking up space. The ones where you can get into a bit of a problem, we call the midlife crisis, it's a cute term, is when you have objects that live for a few seconds or a minute or something, and they end up in Gen 2 and then they're garbage. As Gen 2 gets more and more garbage in it, the garbage collector runs and it says, hey, it was profitable to do a Gen 2 collection. I'll do another Gen 2 collection before too long. And you can end up with a lot of these more expensive Gen 2 collections. If you suspect that you're spending a lot of time in the garbage collector and seeing these kinds of problems, I encourage you to use the perfmon tool and the CLR profiler that Abhi will talk about in much more detail to diagnose these problems. What are some other common pitfalls that we see again and again inside Microsoft with people using garbage collection? The biggest one is just leaks, inadvertently holding on to large object graphs. This happens, at startup time, you build some structure to initialize something else, and you forget to let go of that structure, and the garbage collector dutifully preserves it for all time for you. In some cases, it's helpful to discover these things, again with the CLR profiler, and just null out a reference or two, and that lets the garbage collector discover it's all garbage. Boxing can be a problem sometimes. Boxing is when you have a value type, such as an integer or an enum or a struct, and you assign it into an object. This often happens if you put value types into object collections, like ArrayList or hash table. And we have to box the object. That's a process of copying it into the garbage collected heap, and then it becomes something which drives garbage collections, and the garbage collector has to manage. It's much cheaper if your value types stay on the stack, and they're automatically reclaimed when you return from the function. So you have to watch out for those. Pinning is something that happens when you lock down the address of an object, either for unsafe code or calling out down to native code as part of interop. And if you pin a lot of these young objects and a garbage collection happens, it kind of ties the hands of the garbage collector, which can't make these nice contiguous zones anymore. It has to leave these little sandbars of pinned objects. Some folks sometimes resort to calling gc.collect explicitly, and that kind of interferes with the very nice automatic self-tuning garbage collector. It certainly causes more collections than are probably profitable. So we generally encourage people who are tempted to do this to not do it. And then finalization deserves its own slide. Finalization is a facility that you can use to clean up native resources. So if you have a managed object that's holding onto a native resource such as a bitmap or a file handle or something, if that managed object was just collected as usual, you'd leak that handle. You wouldn't have given it back to the operating system. So with finalization, and the syntax in C# is this tilde class name syntax, we promise to call your finalizer object after the object is found to be dead or unreachable. The way that works is we do some bookkeeping on these objects. We note the objects that have finalizers. When we do a collection, we take the finalizable objects and we say, oh darn, I have to remember to call this guy's finalizer. And I can't do that now because I'm doing a garbage collection. So we promote the object into the next generation even though it's unreferenced. We queue up a call on its finalizer that will be run later when we're out of the garbage collector. The worst thing about promoting the object into the next generation is any objects that it references, which are maybe also dead, also get promoted into the next generation. So the costs of having a finalizable object can really add up. And so as I say here, it's an expensive facility and you should use it sparingly. If you have an object with a finalizer, there shouldn't be anything else to the object. You shouldn't hold a lot of other object reference fields and so forth. It's probably profitable to split that object into a managed object that doesn't have a finalizer and an object with a finalizer that just holds that native resource. To reduce the cost of finalization, but also to have the safety of the finalizer in some cases, there's something called the dispose pattern. If you have an object like this, you should probably implement it. In a nutshell, what happens is you implement the iDisposable interface, which has just one method called dispose. Your dispose method should do your native resource cleanup, and then it should call gc.suppressFinalize. This tells the garbage collector this doesn't have finalization semantics anymore. You can just reclaim the storage if you find this object dead. Then in code that's a client of such an object, if you are using it in a setting where you make it, you use it, you don't give it to anybody else, you're done with it, that's a setting where you should call dispose on it so that you can very early reclaim the native resource and continue and remove the finalization cost. In C#, there's even special syntax for this called the using statement. You say using and then your object allocation, and that gets turned into a try finally block or something so that no matter how you leave that code, the C# compiler will dispose your object for you. Okay. The next worst set of pitfalls after memory problems are what I just summarized as indiscriminate code reuse. And you're going to see this theme throughout the rest of my talk, actually. So we can make the CLR as fast as we can, but you're making choices up in the layer above the CLR about what code you're using and what approaches you're taking to solve your problems. So you're making algorithmic choices, architecture choices, but you're also choosing to use this facility in the .NET framework or this facility in some component you've got. And unfortunately, inside Microsoft, we keep seeing poor choices. People have used an API in a setting where it's too expensive. Many times, you can use an API and it's just fine. But in a hot spot, in a critical piece of code that gets called over and over again, that's too expensive to use. There's something about managed code which exacerbates this problem, and I think that because coding is easier, because it's easier to reuse other people's code in managed code, it took away some useful friction that we had in the native world. If I wanted to use your library, I'd have to go look at its source. I'd have to say, how does he allocate objects? How does he handle failure, etc. In managed code, especially through the .NET framework, we have a common allocator. Don't worry about freeing. We have a common exception discipline, etc. So I can just use your code even though I don't know anything about it, and it'll probably work. But it may be too slow. So you do have to work on this. I say that you have to do your homework, borrowing a term from our colleague, Rico Mariani. You really have to understand, in the code where it's most critical, which is not all your code, it's maybe 5% of your code, you really have to understand what the performance implications are of using that facility in this place. And in some cases, it means you have to go and do some measurements, because we're not great right now at telling you what the different APIs cost in different settings, which is, by the way, a very hard problem in general. So if it really matters to you, you should go and measure with timing loops or with any of the tools that Abhi will be talking about to see what this thing costs and can I afford it here. If you do that one thing, you'll never be surprised, oh, I didn't realize that all that was happening, and your code will be that much zippier. The next worst category of problems we see inside Microsoft performance-wise are two categories of what I call data pitfalls. The worst one is data locality, right? So you have this machine, it can do 1 billion or 5 or 10 billion instructions per second, but it's waiting. It's waiting on some remote thing to happen. And unfortunately, we see that even though we can do, access a cache in a nanosecond, when we start going to DRAM, that can, as soon as you're off chip, that's 100 times slower. If you have to pull something off disk, it's 10 to the 7th time slower, and if you have to go remote, it's even worse. So you really have to look at the critical data that you need and make sure it's close enough to meet the performance requirements that you need. In some cases, you need to make a copy of the remote data locally, or on a background thread, you have to bring in some data from disk into RAM. And in some cases, you have to even worry about cache locality and do the critical data structures fit in cache. And by the way, talking about that, the garbage collector, because it allocates objects from these contiguous free areas, will tend to put new objects together in contiguous memory addresses. And because when it slides live objects down, it doesn't reorder them. That gives you the nice property. The data that's allocated at the same time will stay together in the same memory addresses. And sometimes you can use that trick to get some things packed on a cache line that you can't otherwise do. The other kind of data pitfall is data representation, choosing a poor data representation. And the poster child for this is misuse of XML. So XML is a fantastic facility for interop. How am I doing for time? Running a little time. XML is a fantastic facility for interop. However, it gets used in ways that you wouldn't have imagined if you were writing native code. It frankly has uncompetitive performance with respect to native binary record-oriented formats. We have some examples in our libraries. So you have to ask yourself, do I want to be fashionable and use XML, or do I want to have a zippy app that my users will appreciate? Most of the time, your users don't care that you're doing XML under the hood. Reflection is another of these really cool, very useful facilities that you can use to do dynamic wiring up of stuff. Some parts of reflection, like getType, are pretty good. But other things, when you start getting reflective methods, fields, when you start setting fields reflectively, when you start invoking methods reflectively or creating objects reflectively, you're getting at least 100 times slowdown compared to just saying a.foo equals blah or calling a method or newing an object. In addition, there's some memory footprint issues with reflection because we have a lot of managed objects that stand for all this stuff. And under the hood in the CLR, we also have to bring in a lot of metadata to support that reflection up top. So there are cases where you can't afford reflection, and be aware of that. It's also a fairly insidious thing, and it can sneak into your code if you're doing late bound stuff. And there's some options you can set here to help you not do that in VB. If you have reflection issues, you may want to rewrite to avoid it. In some cases, you'll just need a switch statement where you do the same function unreflectively, or you may want to generate some code and run that code instead. Interop is another one that we sometimes get performance issues with. One of the nice things about the .NET Framework platform is that we let you leverage your existing native code investments. It turns out that the raw interop call from managed to native or back is quite efficient. But if you make a lot of calls, those costs add up. And if you marshal data types that are not a nice match between the managed and the native domains, that we have to do copying and things, those costs can really add up. If you think you might be having interop things, if your app is very heavy with interop, you can use some perfmon counters that tell you about the number of interop calls and the number of marshalling events that happen. And if you are having interop problems, one thing you can consider doing is changing to interfaces that are more batchy or chunky, where you give a whole lot of units of work between the one domain and the other with a single call. Or you can move the boundary. You can either move some code that's native into managed, or you can take some code that's managed and move it down to native. Some of these are quite easy with managed C++. The final pitfall category I'm going to talk about are what I call deployment pitfalls. Now, when you take your managed code and you compile it, you end up with these assemblies, these ILDLLs. And assemblies, you make many, many assemblies for many reasons. Whether it's that you're building some code and I am, so it's natural to make two assemblies. That's kind of separate authoring leads you to have multiple assemblies. But sometimes you choose to have multiple assemblies for versioning considerations, security, encapsulation, etc. There's all kinds of reasons that you want to have lots of assemblies. Some of our tools, like TLB imp, make you have lots of assemblies. The bad news performance-wise is there's an overhead to loading all these assemblies and reasoning over them and finding them on the file system and so forth. And so we encourage you to try and have as few assemblies as possible and still get these other requirements that you have. In some cases, it's helpful to merge assemblies together. Now, if you have a dozen assemblies, that's probably not bad. If you have 100, you should be really worried. And we've actually talked to some customers that are loading 1,000 assemblies, and you really don't want to do that. Okay. Another thing you should do is know what assemblies your application is loading and when it happens. You can do that with debuggers. You can do that with the VS, etc. You can watch them come in. You can say, why is that happening? Two other topics I want to talk about. One, if you have strong name signed assemblies, each time we run that assembly, we're going to check that the strong name signature is still valid. That can be a problem on startup paths. So although our advice in the past has been to put things in the GAC, the global assembly cache, only if they're shared. If they're strong names signed, it may help your performance to put those in the GAC too. And the final topic I'm going to talk about briefly is NGen. NGen is actually, a whole talk worth of information. And we're going to have to get some more, it's clear we're going to need to get some more guidance out on how to make the best use of NGen. NGen is the ahead of time code generator. So if you don't want to wait for JIT to happen when your code is run, you can NGen it. That takes your assembly and it runs the JIT compiler to populate and generate all of the methods in your code into a DLL that gets cached in a place called the NGen image cache. Using NGen, particularly the NGen that's in Visual Studio 1.1, may reduce your startup time. It may improve page shareability if you have components that are loaded in multiple processes. Currently, the NGen image code may run a little bit slower, a few % slower than native code. I would encourage you just to try it for yourself and measure it. You may get a benefit or you may not. As I'll talk about later in the talk, we're making heavy investments in NGen, both in Whidbey and in the Longhorn era, to make it get much better results. Okay. I'm now going to turn over to Abhi, and he's going to talk about how you can diagnose some of your performance problems and what tools you use to do that. Abhi.
Thanks, Jan. Hi, everybody. This is my first TechEd, and it's great to be here. We're getting good performance feedback from some of you, and please keep that coming. So today, I'd like to show you some of the tools and techniques that my team uses when we analyze performance problems. First of all, even before looking at a running application, it sometimes pays to look at the code itself. Now, in many cases, you might not have the code of the .NET Framework assemblies or some other third-party assemblies that you're using. In such cases, ILDASM is a great tool to get a feel for the cost of the API. For example, you can stream the IL into a text file in grep for or findStir for box, and just find locations where unexpected boxing might be occurring. Debuggers are another good performance tool because you can look at all the assemblies that are being loaded, what stack traces loaded them, And if a particular assembly is getting rebased, then the debuggers would tell you that. The debuggers are also cool because they tell you, they can show you the actual JIT compiled x86 code. And that can be sometimes helpful to give us feedback as to what the JIT optimizations are being done or not being done. And the third code inspection category tool that I want to mention is the FXCOP. FXCOP is a static code analyzer, and it looks at your code, and we've built a lot of performance expertise into the FXCOP tool, and it can give you performance warnings. And you can use those warnings. Either you can go back to your code and try to eliminate them, or at least be aware that there is a performance issue with this piece of code. Well, not everything can be done with just inspecting the code. So when you start running an application and you see that you have a performance problem, it's slow to start up, or it's slow response time, and so on, you need some good tools. Now, one of the problems that we always find ourselves getting into is that we try to tune one part of the system, and we still do not see an overall performance improvement. That's because again and again, we find that we are not looking at the right area to go and tune performance. That's why over time, we have learned that it's very important to look at your whole system as a whole and then drill deeper into the problem areas. Now, Task Manager is a good tool. It can just eyeballing Task Manager can tell you whether you're CPU bound or whether there's some memory issues and so on. The next overall tool to use, and very non-intrusive, is perfmon counters. I'm sure all of you have used perfmon at some point, and now we have added .NET CLR counters. Actually, we have added them since version 1 into the perfmon tool. And so those counters are excellent to give you a good idea of what the problem might be. The third tool is VA dump. It's the virtual address dump. It's a tool that you can find on MSDN. And it shows you the memory usage and the working set characteristics of your application. It can tell you more about the GC heap, how much is being allocated on the unmanaged NT process heap, what sort of assemblies and how many pages from each assembly is loaded, how many are private, and so on. I'll show you that in a minute. And finally, the overall overview tool that I'm talking about is ETW, which is Event Tracing for Windows. And there is some support today in v1.1 of the CLR for ETW, but a lot more is being added in the Whitby timeframe and Longhorn. So once you figure out, once you see that, okay, perfmon tells you that there's a high CPU utilization and even the task manager confirms that, then you need to go and drill deeper. One of the tools that we use is a sampling profiler, which we have started building right into Visual Studio Team System 2005. And we use those to figure out what hotspots, what methods are showing up on the top. And then sometimes we can either tune those methods or we need a call attributed profiler. Again, we are building that into Team System 2005 to see whether we're calling some functions too many times, and that's why those functions are more hot. If VA dump shows that there is a lot of usage in the GC heap, then you can use specialized tools like CLR Profiler. I'm going to demo that soon. For unmanaged process heap, there's a tool called UMDH. Again, you can find it on MSDN. And that's a great tool because it shows you the stack traces that allocated unmanaged memory. So let's jump into a demo and see what sort of perf counters and what sort of analysis we can do. All right. Let me open up my project. A pretty simple code. I start a timing loop using the query performance counter class that Jan just showed you. And I have 500,000 iterations. And in a for loop, all I do is I create two kinds of objects. One is a system.drawing.solidBrush, and another is a string of a length which is based off on the index. Ideally, I would do some work here, and today I'm not, but this is just to show you some of the tools. I stop the timer, and I print out the time. And then I wait for my input so that I can show you some interesting perf counters. Let's go ahead and compile it and run it. Took 1.31 seconds. For perf benchmarks, it's a good idea to run them a couple of times just to make sure that you have stable numbers. Looks like 1.27, 1.29 seconds, right around there. Okay, so as I said, let's use a top-level tool like perfmon counters to see what's going on. And 1.29 seconds for a million allocations, not too bad. Maybe there's no perf problem. Okay, perfmon, let me add some of the commonly used .NET CLR counters. They're built in right here with all of the counters. For example, today I'll add the number of exceptions thrown for my demo2 instance. I will also add the number of bytes in loader heap. Loader heap is a CLR heap where we load all the classes into. So that's interesting for us. We'll add the GC counters, which are called .NET CLR memory counters. They're very interesting usually, so I'll go ahead and add all the counters. And say the number of security checks. Okay. So let's look at these counters one by one, and keep in mind that after all the loop iterations are over, we are actually stopped right after that point. So the counters are a snapshot as to the last events that happened inside CLR. Some of the counters are cumulative. Number of exceptions thrown counter is 0, and it's a cumulative counter, and there are no exceptions. Good. We have about 176 kilobytes in the CLR loader heaps. Not really a very big deal right now. We have about 354 bytes in the GC heap. Again, nothing remarkable. Let's keep going. The number of Gen 0 collections is 278, and the number of Gen 1 collections is 46. Now that's a ratio of about 6 to 1. You did 6 Gen 0 collections for 1 Gen 1 collection. Now, the guideline that we give is that we would like to see 10:1. So for 10 Gen 0 collections, we would like to see 1 Gen 1. And similarly from Gen 1 to Gen 2, which means that if you have 100 Gen 0 collections, typically you should see no more than 10 Gen 1 collections and 1 Gen 2 collection. Gen 1 and Gen 2 collections are more expensive, which means that if you're seeing more of them for per Gen 0 collections, then you're paying more GC cost. So in this case, it's 6:1. Let's keep going. Performance investigation is like crime scene investigation sometimes. You need to piece together clues, and sometimes the picture gets clearer as you discover more and more problems. So that's 1. Let's keep going and look at, there's one more that catches my eye, and that's the finalization survivors. This is a per instance counter, and actually the help from perfmon will tell you that. This counter was last updated on the 278th Gen 0 collection. So they were on the last GC, there were about 1,800 objects that survived finalization. Now, just doing some math, if you multiply the number of Gen 0 collections with the number of finalization survivors, we would get a number which is close to 500,000. So again, this is clue number 2 that there might be something going on, and we had 500,000 iterations. So there might be one object per a loop that is waiting to be finalized, and hence getting promoted. Let's also confirm that and look at the promoted finalization memory from Gen 0 to Gen 1, and that's 64 kilobytes. And again, that's a per GC update. That count gets updated per GC. So 64 kilobytes of memory got promoted from Gen 0 to Gen 1 for finalization in the last GC. Again, multiplying that number with the number of total GCs gives me a rough feel, and that number is 17 megabytes, gives me a rough feel of the total cumulative memory that moved from Gen 0 to Gen 1 in this run of this application. One small thing, for example, if you multiply the number of Gen 0 collections with the Gen 0 heap size itself, which is 164 kilobytes, that comes out to roughly 45 megabytes, which is the total allocations done in this application. Anyway, the other thing I wanted to show you was the top-level tool of VA dump for this application. VA dump uses the process ID. So let me pull up Task Manager, demo 2, 3028. S is for summary, output, process ID, 3028. And let's look at what the output is. First of all, it shows me the grand total working set. It's 8096 kilobytes, roughly 8 megabytes. And then it shows me a split up. About 4.8 megabytes was in the modules, about 3 megabytes was in the dynamic data, and 148 kilobytes in the system overhead. And it further gives me a split up of the dynamic data of 3 megabytes as heap stack. And so heap is 772 kilobytes, thread stacks is only 48 kilobytes, and so on. And this other data is the category in which GC heap lives. Going forward, we would call that out separately. But today, other data lives in GC heap. So our GC heap is in this 1.8 megabytes. Anyway, so just to give you a feel for this tool, if you see this heap number growing up, then you know that you have an unmanaged memory leak. It's possible that that's because you're holding on to it from either your unmanaged code or even from some managed code using handles. And if this is going up, then you know that you have a GC memory leak, and I'll show you some of those, some of the tools that can help you identify what that is. And finally, we have 4.8 megabytes of modules. They're listed right here. Great. So just looking at the perf counters, we have already figured out with the 3 clues, the 6:1 ratio, the number of finalization survivors, and about 17 megs of finalization memory getting promoted. We should use something which looks at the GC heap, another tool like CLR Profiler, to nail this problem and to confirm what we fear. So let's run CLR Profiler. Again, CLR Profiler is a free tool. I don't want to profile calls today, just the allocations. Let me start the application. CLR Profiler is based on the profiling services. So it does run about 10 to 15 times, or actually it can run much slower than that when the application is running from within the CLR Profiler. However, it does work for WinForm apps, console apps, ASP.NET apps, and other services. It cannot be used for production services, production machines, because it is intrusive. But I'll show you a workaround later on. Anyway, so our app finished. And the first view that the CLR Profiler brings up is this allocation graph view. And maybe you cannot see it, but I'll just point out that 26 megabytes of string and 17 megabytes of solid brushes got allocated. Now, tying it back to the previous perfmon counters, we saw that 17 megabytes of memory was finalized. It's possible that solid brushes are the ones which are getting finalized. And indeed, solid brush objects have a finalizer. But we'll keep going, and I'll show you some other neat tricks to find that. The total memory allocation was 43 megabytes. Again, we saw that number of Gen 0 collections multiplied by the size of the Gen 0 heap was about 45 megabytes. Let's go and look at some other views of CLR Profiler. The second view that I would like to show you is the histogram of allocated types. It tells you right here, the yellow objects, the legend on the right shows me, are solid brush objects. The red objects are string objects. And no surprises, we see only these two kinds of objects in the histogram of allocated types. But the next interesting view is the histogram of relocated types. Relocated types are the types that are moving from one generation to another. And they could move for a couple of reasons. One is that they have a finalizer on them, and then the garbage collector cannot collect them because it's not pure garbage. And they also need, the second reason why memory might move from one generation to another is because some real references are holding on to them. So here, surprisingly, actually not so surprisingly now, we see that solid brush objects are the only relocated types. Let's keep going. There's a module graph view. I'm not going to show you that today, but that can show you the modules loaded, and you can see what stack traces loaded which assemblies and which modules. Let me show you the timeline view. The timeline view on the x-axis gives you time as it's increasing, and the x-axis is also annotated with these garbage collection numbers, and they're color-coded. So the red ones are Gen 0 collections, the green ones are Gen 1. And some of these are missing. For example, you do not see a GC number 5. That's just a resolution problem. If you expand it enough, you would see them. And on the y-axis is address heap growing, the heap growing up. So let's scroll to the right. And you'll see that I see these patterns being repeated. Let's try to figure out what these patterns are. Now, this is what we call a double sawtooth pattern. You see that the red objects and the yellow objects, again, red objects are the solid brush objects and the yellow objects are the string objects. You see that both red and yellow objects get allocated, and then there's a dip, which is actually a GC collection. But the yellow objects do not survive that, but the GC squishes all the red objects and forms the next step, and they seem to be sticking around. And this keeps growing till a Gen 1 GC happens, the GC number 54 in this case, if you can see that. But till a Gen 1 GC happens, and then we reclaim all that memory. And then we start the same pattern again. So as I explained before, this is what's going on. The system.drawing.solid brushes are hanging on till a Gen 1 collection happens. They get promoted into the Gen 1. The finalizer thread gets a chance to run. It runs the finalizer, upon which those objects are truly garbage now, and the next Gen 1 collection collects them. All right, so what should we do? As Jan mentioned, we should use the dispose pattern to fix this problem. Let me quickly do that. Let's call b.dispose. Save it, compile, and run it. 0.62 seconds. And we had 1.29 seconds previously, a 50% increase. Had I looked at that code, just that loop, I could have done JIT optimizations, or I could have thought of optimizing for memory and in other ways. But tools help you really identify the real problem. And in this case, that was hidden behind and happened to be the finalization problem. There's one more thing that I'd like to show you. Actually, let's go back and look at the CLR profiler again. And for this optimized app. Again, it's going to take its time because it runs slowly under CLR Profiler. CLR Profiler, as I said, is a free tool, but in Visual Studio Team System, Visual Studio 2005 Team System, we are integrating a lot of these features. So check that out. As before, it brings up the allocation graph view. Nothing has changed here. We're still allocating 45 megs. But let's go and look at the relocated types. And we do not see that red bar. Let's also go and look at the timeline view. These radio buttons at the top, let me zoom into some. So this time, I see a single sawtooth pattern. And that's a good pattern because at the end of the sawtooth, the entire memory comes back to the pre-sawtooth levels, which means that nothing is surviving into generations and not living long. And the garbage collector's performance for short-lived objects is pretty good. All right, so as I said, CLR Profiler is pretty intrusive, so you cannot use it for maybe real live servers, but there are other ways in which you can look at some of the problems. And one of them is attaching a debugger, taking some dumps, then offline and analyzing some of the properties and some of the things that CLR maintains. One of those is the NTSD debugger extensions. So let me go ahead and modify my app a little bit. Let me uncomment these two lines, which make me stop before my loop starts. Let me go back to the problem itself. Compile that. And let's launch it under the, let's run the app first. And let's attach a debugger. Again, I need the process ID. 3040. Okay, so right now the app is waiting to be started. It's as if your production server is going or your live machine is going. You can attach a debugger quickly, break into the debugger, load this strike extension, which you can again download from my blog. And let me show you the help for strike. For those who don't know about NTSD debugger extensions, these are debugger extensions that can let you look at the process memory and reason over that memory and show you some stats. There are many commands here, and I'm going to show you two of them today. One of them is dump heap, that dumps the GC heap contents. It has an optional parameter -stat that gives you statistics. And the other one is the finalize queue, since we know already in this case that we have a finalized problem. So let's look at dump heap -stat. Shows me that system solid brushes and strings are on the, and then let's look at the finalize queue command. It shows me that those many system solid brushes are waiting to be finalized. Anyway, so to sum up, we have seen some tools, but the most important part is make sure that you're looking at the right problem. Don't get misled and try to fix a wrong problem. Do a top-level analysis, use perfpon, use VA dump, and then use specialized tools like CLR Profiler to drill deeper. Thanks.
Fantastic. Thank you, Abhi. Am I on? Thank you. Good. So just a couple of slides to talk about what we've been working on for CLR performance, looking towards VS 2005, and then what we can look forward to in Windows Longhorn. Here are some of the things we've been doing in perf work on the CLR. Some of you have been spending a lot of time calling between app domains, and we realized that we needed to tune that up. So that's between 1 and 50 times faster calls between app domains using .NET remoting, depending on the types of arguments being marshaled. We've also dramatically sped up the creation of delegate objects and invocation of them. One of the big new features in the CLR for .NET 2005 is, of course, generics. And generics have the potential to help you avoid a lot of boxing and casting. So we have in the new base class libraries for generics, we have list of T, dictionary of key, comma, value, and those collections are tuned for the specific type parameter that you've done the constructed generic type on. So these, when you put objects into them, we don't box your value types, and when you take them out, we avoid the casts. We've also tuned up for each loops over these things. We avoid a heap allocation for the enumerator object. We have another nice facility if you've been using reflection emit called lightweight reflection emit. With lightweight reflection emit, you can emit a single method. You can populate it with IL. You can then turn it into a method that you can call as a delegate. So if you wanted to use generated code to glue some things together or to have some data-dependent code generation, this is a nice facility. When you're finished with this delegate and you just release references to it, a garbage collection will clean up the delegate and the native code behind the scenes. So it's part of the way to being able to unload some bits of code. It's quite nice. In the garbage collector, we fixed some problems that we have in .NET 1.1, and someone actually brought one of them up the other night. So the first thing we've done is we've added a memory pressure API. So if you had this little 20-byte object that was holding on to a 1 megabyte native bitmap, the garbage collector has no way of knowing that it would be very profitable to collect, not just to recover the 20 bytes, but to recover the megabyte behind it. So if you're doing these kinds of things, you can use the add memory pressure API to inform the garbage collector that more collections might be profitable. We've also fixed some of the pinning issues that we had in the .NET 1.1 product. If you have a lot of pinned objects creating these little sandbars, we would sometimes allocate memory and run out of memory. And in the forthcoming CLR, we're able to reuse the bits of memory between the sandbars. Now, looking ahead to Windows Longhorn, there's going to be a lot of managed code running in that platform. The new GUI libraries called Avalon, the new web services stack called Indigo, and the new storage stack called WinFS are using a lot of managed code. You're going to have managed code operating system DLLs. Okay? Now, we can't go and for every new process you start up that uses Avalon or Indigo, for example, go and JIT another copy of that code because it would be private memory and it would take up a lot of memory per process. We need to minimize the marginal cost of these things, so we use an enhanced engine that we've been working on and will continue to work on in the next development time of Longhorn to tune that up. Our goals on this are for the managed modules, which is your native image DLLs, to reduce the working set costs by half and to reduce the private pages by half, and they multiply those benefits. And so when you start another managed process, you'll already have in memory the CLR, the .NET framework, the WinFX code will already probably be loaded by Explorer or some other managed process. And so the time to start that next process will be quite low, and the memory that's specifically incurred by that next process will also be low. Ultimately, I've already told you that managed code can rival native code on raw execution speed, but we're also working on these other metrics of startup time, working set, and private pages to rival native code in those areas too. So to summarize, I'd like you to aim high, to not use managed code as an excuse for mediocre performance. You can get great performance in managed code if you're careful. Again, that mantra is to set goals for your application development process, measure where you're at all times with automated tests, and know the cost of the platform facilities you're using. Watch out for pitfalls. We've shared with you the pitfalls that we see happening over and over again across internal Microsoft development. We talked about memory management problems, indiscriminate code reuse, overuse of reflection, overuse of interop, overuse of XML. We didn't talk about exceptions, but exceptions in managed code are more expensive than native, so watch out. And deployment issues around lots of assemblies. And we've talked a bit about NGen, which we're working on to make it better and easier to use and easier to succeed with. Get into the culture of measuring. Get some of these tools that Abhi was showing you or some other fine third-party tools. Learn how to use them, and you can get great new insights that you have to have if you're going to get great, fast software. Finally, what we're trying to do with the CLR is make it not only a great platform for rapid application development, a very productive and a great place to write code, but also make it a great platform for hardcore systems programming, where every cycle and every kilobyte counts. Okay. in terms of resources, we haven't mentioned this, but there's this fantastic new, really thick book, which is also online, from the prescriptive architecture guidance folks at Microsoft called Improving .NET Application Performance and Scalability. This URL will take you there. Down in the exhibit hall, if it's still open, they have a few CDs like this in the prescriptive practices booth, which has a copy of this on it as well. There's some great material. Much of it was contributed by our colleague Rico Mariani about these kinds of problems and other problems that you can avoid. We have a website here with links to a bunch of white papers and tools like CLR Profiler, which, by the way, also has a 100-page tutorial which shows you how to find other problems like leaks. There's a news group. We have some blogs. Sorry, mine's been kind of idle. And we don't have time for Q&A here, although we'll be mulling around out front, and then we're going to go over to Cabana 5-6. We'll be there for hours. You can catch us there and ask any questions that you might like. Please fill out a session evaluation. So thank you very much.